Let me reset that recording. All right. Good. So, just a little bit of, let me unfreeze this. Just so you guys know, exam is going to cover review of statics. So you guys should know your statics for the exam. It's going to cover stresses, so like normal and shear stresses. And then it's going to cover what we're going over today, which is normal stresses, normal strains and deformations, as well as what we're going to cover next class, which is going to be shear strains and deformations. We will have a review. The review is going to be next Tuesday. We'll just be doing constant problem solving just so that way you guys feel prepared. And of course you guys we can go over homework problems too if you guys had any questions. But I will be uploading all of the homework solutions by Thursday, just so that way you guys, can watch those recordings and feel more prepared. But you guys can also always contact me for questions, or if you guys have specific problems, we can just meet after class or before class just to do some additional problems. Yes?
How many questions usually are on an exam?
I am going to be putting 5 questions on the exam. Question 1, my students hated last semester because it's true and false questions. And the way that the true-false questions work is you get 1 credit out of 20 points towards, or is it 10 points? I think it's 10 points. Basically, you get full credit if you answer the question right, no credit if you don't answer the question, and you get negative credit if you get the question wrong. Which means if you absolutely blow the exam, the worst you can do is a -5 on the exam. So this true and false questions, the best thing I can tell you is don't guess. All right? Because then it's a 50-50 shot of you getting full credit or losing more credit. All right? Are there any other questions about that? All of the other questions should just be like the practice problems that we've been doing in class. Make sense?
Sure.
Yep. And you guys have the full time. And usually I would provide an appendix, but I'm thinking this semester I'll just let you guys use these packets that I printed out for you just to save on paper. And then you guys will also get a flashcard from me that you guys can use for the exam. You can put basically whatever formulas you want on there, just no practice problems on those flashcards. I'll be checking everything just to make sure. Any other questions? Yes?
Do you get partial credit too?
Absolutely. Yeah, no. The questions aren't like multiple choice or anything. It's only the true-false questions that are just kind of like, it's either a hit or a miss. But everything else is going to be partial credit because, I don't feel that, if you do your entire procedure right and your number you messed up a number somehow from like the calculator, you shouldn't get the entire question wrong. So I'm looking more at what the procedure is more than anything, making sure you guys are following proper steps because, even professionals make calculator mistakes. It's why I have like 3 people looking over my work whenever I'm submitting stuff to contractors, especially since half of my calculations are over like 500 pages long. All right. So today we are going to be talking about the relationship between stress. Is it? Oh, well, the one on the right-hand side is, but the one on the left is not. Stress and strain. There we go. So, let's just start off by simply considering a basic bar. Right, this bar is subjected to some force. We're just going to call it just F. We don't know what it is. It could be anything. Right? Now, we learned last lecture how to determine the stress within the bar. So, what is the stress going to be equal to? Let's say it's circular and cross-section with some area A. What is the equation for stress? Yeah.
Force over area.
Yeah. So we would just get the stress is equal to just force over area. Now, what's something that was never really considered when you guys learned statics? Like, what were some of the rules that you had? Like, one of the things was like your members are considered rigid when you're designing a structure, right? All right. Is that actually the case in practicality? No. Your structure's deformed. So we have this new concept, which is going to be called strain. And strain and stress are related to each other. I'll get into that a little bit later. But strain is defined by this Greek letter we call epsilon, which is basically just a backwards 3. And that epsilon is equal to the change in length, delta, over the total length, L. I will just move this really quickly just so I can show you guys what those terms refer to. So the bar is just going to be some initial length L, right? That's the undeformed length of the bar. And then as you pull on this bar, it's going to change in some length here. And this dimension here is that value delta. So it's change in length divided by the original length. So let's just start off with an example. Let's say we've got a bar that deforms by about 0.5 inches. And this bar has a length L equal to about, 8 feet. What would the strain equal? Let me make sure I've got the audio working on this thing. Yeah. Anybody want to take a crack at it? Yeah.
0.0625.
What are the units?
Feet.
Nope. You got the number right, but the units are going to be inches per foot. Now, I'm going to warn you guys something with this. We always try and keep the units for strain the same. So it's going to be inches per inch. That's how strain is usually measured. So in reality, whenever you guys are asked to solve for a strain, don't do that. Instead, take the 8 feet, multiply it by 12 inches per foot to get it into inches as 96 inches. And then let the strain equal 0.5 divided by 96, which gives you 0.0052. And what you notice is the inches on both the denominator, on the numerator and denominator, they cancel out, meaning that what are the units of strain? It's unitless. It's a unitless quantity. So strain has no units, and it should always be expressed in terms of a way that the units should cancel. So if you get meters per millimeter or millimeter per meter, don't express it that way. Convert the meters into millimeters and make sure that the units cancel. All right? Good. So we know that strain has to be unitless. let's now talk about the relationship between stress and strain. So the question becomes, how are stress and strain related? Now, does everyone have their little packets here? If not, I recommend you take them out. It's going to become important really quickly. Everyone got their packets out? Now, I would just turn to one of the pages on Appendix C specifically. That's going to be very important in just about a second. So, let me know when you guys are ready. Just raise your hand when you're ready. 1, 2. Sweet. All right. So the way that stress and strain are related is through this thing called the modulus of elasticity. You guys will see it. It's 1, 2, 3, 4, 5, 6, 7 columns from the far left. So it should be in that second to last block where the lines kind of separate everything. You guys see it? Let me know if you can't see it. This modulus of elasticity we call the letter E is a material-dependent property. It's basically a measure of how stiff a material is based on the material property itself. If you guys think about it, let's say you've got a 1/2-inch diameter bolt of steel versus a 1/2-inch diameter bolt made out of, I don't know, like aluminum. What do you guys think is going to be stronger, the bolt of the same size that's in steel or the aluminum? What do you guys think? If you don't know, look at the table. Well, the steel is. Steel is going to be a lot more stiff if it has the same properties. Now, let's say that the aluminum, you increase the size of the bolts. Now you have the geometric property in play with the stiffness as well as the material property. And this is really all of the stuff that we need to play with when you're designing things, is what size do I need it to be? What material do I want to use? How stiff are these elements going to be? And are they going to be able to carry the load? Are they going to be able to limit the amount of deformations that are occurring? Because all of this needs to be considered when you're designing a building, right? You don't want to be standing on a steel beam that's going to be deflecting a foot underneath you, right? Or bouncing up and down as you're walking on it. That's not a very stiff connection. What you want is something that you can feel comfortable with while having the members still being able to structurally support you, right? Good. Now, how is this elastic modulus obtained? What I want to do is just look up on here. A uniaxial tensile test. Let's see. I think this is a good one. I have no idea if the audio is playing on there, but I don't care. So this here is something that we call a test coupon. Basically, when you are running a bunch of these tests to obtain like material properties, what you have are these things called stress and strain curves. These stress strain curves are really important because they help us understand the material behavior at various loads and deformations. How do they relate to each other, so on and so forth. So I'm just going to play it. And what you'll begin to kind of notice is right on the diagram, you'll see kind of everyone can see it, right? So we're adding more and more stress and strain. And right there, you guys will notice there's kind of like a plateauing that's kind of occurring. The important thing to note here is that linear portion of that diagram that was just produced. So let me come back to here. So what we've got right now is this diagram. That's so small. And then we've got these data points here from the stress strain curve that just go up linearly, right? Stress was plotted on sigma on the y-axis, and strain was plotted on the x-axis. What this elastic modulus is it's the slope here, which is how it relates the stress to the strain. So what we say is that the elastic modulus, once you do all of the math and figure it out, is equal to the stress divided by the strain. Are there any questions about that so far? All right. Now, let me just continue playing this a bit more. What I do want to note is we're going to be sticking primarily in this region when we're designing stuff. A lot of materials, you generally only have this curve. What you guys will notice is this material is steel, which has a very unique property in the sense that it undergoes additional stress after it's yielded. So what you guys notice is the true stress versus engineering stress strain. The engineering stress strain, I'm presuming, is... No, never mind. Ignore what I said. So the engineering stress is what we design with. This assumes that the cross-sectional area remains constant as we're designing material. But what's happening as you stretch it? Like, what's happening to the cross-section? The cross-section is slightly changing, right? You could think of it like if you're pulling on something, the size of the cross-section is just going to be getting smaller. And I'll draw that out just kind of like this. So if you're pulling on it, what's going to happen is it'll get thinner and thinner. I guess a better way to explain it is, you guys ever play with Play-Doh? Right? And you guys squish the Play-Doh. What happens to the Play-Doh? It just expands out, right? And then if you were to stretch like the Play-Doh or stretch like gum, like if you take it out of your mouth, even though it's disgusting to do so, what happens? The gum gets thinner towards like the center, right? So it's literally the same exact thing, just obviously it's on a much smaller scale here because the materials are just really stiff. So that's the difference between the engineering stress and the true stress. Is the engineering stress, when we're dealing with it, we generally keep it within this elastic range because it just makes design so much easier. But once you start getting to this point, then you've got a ton of other problems that you got to deal with, and it's like, why even bother? Just keep our design in here. Our math is going to be good enough, right? The numbers should work. So floating Pay close attention to the bottom. You guys see what's happening? Here's like a little diagram showing how the stresses are, or the strains are developing. So you guys notice, once you reach this point here, we call this point yielding. Once the material yields, we generally consider it failing because we don't want the stress to exceed any higher than that. Otherwise, you start running into the problem of really large deformations, which is something we call plasticity. We do not want that usually. And what you'll notice is if you pay close attention to this region right here, I'm going to come over here and just point it out right here, is it's kind of starting to neck. You guys think it'll break when at the point where it's starting to neck?
Yeah.
Yeah, it's going to fracture there. Yep. Literally, there we go. Just spontaneously combusted. But you guys see, for the true stress strain curve, the math is showing it's going to continually keep increasing, right? But in actuality, because you've got the reduction in the cross-sectional area, your stress is actually being reduced because your force, it can't carry as much force now. So it's compensating by deforming more. And obviously it just goes straight down to zero once it fractures, because at that point it's not carrying any load. Make sense? Are there any questions about this at all? All right. So let's come back to the OneNote here. Where is my pen? Tell me I lost it. Where I'm sitting on it. Hope I didn't lose it. I just had it. Did I leave my pen over there? Was it anywhere over there? Oh, it's in my pocket. All right. So I'm going to just reduce this line here. And then I'm going to draw just a straight line across. We consider this an elastic, perfectly plastic model. Where basically once you reach this upper point right here, we call this sigma y, which you guys will notice in Appendix C is the yield strength. So this sigma y is the yield strength of the material. And it's one of the values that we use to design for. So whenever we're designing materials, we generally try and stay within this range and not leave it. Because all of our math that we cover in this class is based on us assuming that our forces and deformations are within this region. Make sense? Now, we have other types of diagrams too. We can have other ones for steel, for example. Steel is a very unique one. That one, I don't really think it was steel. I'm not 100% sure. But steel has this thing where it kind of curves and then it kind of just blows up until it fails. And it breaks there. Here is that yield strength. The slope is still E for that given material. But what the hell is the rest of this stuff? Some materials will be able to carry additional load because of a process known as yielding, which means that deformations will still continue to develop in a nonlinear pattern. And what happens is then they can develop a little bit more strength in order to carry more load. One such material that we use that this exhibits is a steel. And one of the items we would use for basically rupturing strength, which is this peak point up here, or its ultimate strength. So this point up here is called the ultimate strength. Which we'll denote with sigma u. A lot of bolts are designed using this ultimate strength. So really when you're designing really large scale members, the deformations are really important. So you usually try and stick with that elastic region, right? You don't want your 8-foot long beams deflecting too much, because then what happens is serviceability requirements really come into play. But if you've got a bolt, it's such a small cross section, it's not really going to contribute to any type of deformation, right? So because of that, you can kind of get away with using the additional strength that's up here. This ultimate strength is also defined in your Appendix C. So you've got yield strength, which is towards this middle here, and then you've got ultimate strength, which is right next to it. Not all of the materials that have an ultimate strength behave like this curve. This is just how steel behaves, but a lot of materials behave in various different ways with a clearly distinct yield strength and clearly defined ultimate strength. And so it's important to understand the two. Yielding is when you have that bottlenecking kind of behavior, and then ultimate strength is when it's near about to break. Does that make sense? So once it yields, it'll start to bottleneck. Once it reaches the ultimate strength, it's near failure. Any questions about that so far? Good. So, now with all of this in mind, I'm about to throw at you guys a ton of different equations. So, we know now that the elastic modulus, E, is equal to stress over strain. Stress is equal to what? Yes. So F over A, or we'll say N over A, right, to denote internal force. And what was strain equal to? Yeah, or delta over L. So what we get now is E is equal to N times L over delta times A, which we traditionally rewrite to then just say that the deformation is equal to the internal force times its length divided by E times A. And this is a really important equation because now we have a way of relating force to the deformation of the given structure. Let's consider an example right now. Let's say this bar has an axial force in tension of 10 kips the bar has a length of around, I don't know, 4 feet. The bar is going to be rectangular in cross-section, or square in cross-section, 4 inches by 4 inches. Actually, make it smaller. 2 inches by 2 inches. And lastly, this bar is going to be structural steel. And we'll say it's 836, just for the sake of it. We'll call this A, we'll call this B. And what I want to find is basically, what is the change in length of bar AB? Well, let's write down what we know so far. We know what's the internal force, N. What do we have for the internal force here? Say it again. It's 10 kips. In tension or compression? Tension. What else do we know? The length. What is the length going to be?
4 feet.
4 feet. But I would always, when we're ever dealing with these problems, we're always dealing with very small deformations within a certain limit. That's the assumption for this elastic region. So it's usually better to convert everything in terms of the smallest unit. So the length, we can say, is 48 inches. What about the area? What's the area going to be? Yeah.
4 inches squared.
Yeah. And the way you get that is by just multiplying it by the area of the square. So it's going to be 4 inches squared. And the last thing we need is the elastic modulus. What is the elastic modulus of a structural steel element? If you guys don't know, take a look at your appendix.
200.
What is it?
Is it 200?
200 what?
GPA?
Nope. Well, it might be, but we're looking at it in terms of imperial units. So instead of looking at it from the red, no, but look at it from the yellow. Yeah, the yellow tabs, if you are looking at imperial units, look at the yellow. If you see like metric units, look at the red. All right, don't get that messed up because that'll be a big blunder if you mess that up. What is it? Not 29 psi. You guys will notice right where it says elastic modulus or modulus of elasticity, what does it say right underneath that?
GPA.
No, you're looking at the metric. Keep it on the yellow tabs there since we're dealing with imperial. But if you guys read modulus of elasticity right at the top, it says something right below that. What does it say?
10 to the 6.
10 to the 6th, which means that whatever value is tabulated within that column, multiply it by 10 to the 6th. So the elastic modulus for steel is going to be what? 29 times 10 to the 6th, which is the equivalent to about 29 million pounds per square inch. It seems like a very large number, but trust me, it is not really. So the elastic modulus is 29 times 10 to the 6 psi. And then if you know what pounds to kips is, you could just divide that by 1,000, which then will just give you 29,000 kips per square inch. So you could do it one of two ways. You could convert the 10 kips to pounds. You can convert the elastic modulus to kips per square inch. It's really up to you guys. Just make sure that your units are always consistent, because we want this and this to both be in either kips or pounds, and we want all of our units of dimensions and deformations to be in inches or feet, preferably inches, because we're dealing with small deformations. Otherwise, if you get a deformation of like 0.00008 feet, you're going to be like, why the hell is this number so small? Multiply it by 12, even though that's still a very small number, but it makes more sense logically. So we now plug this into the calculator. So delta is just going to equal 10 kips times 48 inches divided by 29,000 kips per square inch times 4 inches squared. And what do we get for the deformation? Is it a large one or a small one? I get 0.004 inches. So it's a very small deformation. Like if we were to plot this on like a stress strain curve, it's probably like way down here. So we've got some wiggle room to really be able to improve the design. All right. Does everyone understand how this kind of functions? Is it making sense to everyone? It's about to get worse. So now, let's consider another example. But this time, I want it to be a stepped shaft. The force here is going to be 10 kips. The force here is going to be 5 kips. The lengths are going to be, 5 feet and 4 feet. I'm going to change the forces a bit. I'm going to use 90 kips, 30 kips, and then I'm going to change these dimensions actually to be 12 inches and 12 inches. And I'm going to say that this is 3 inches in diameter, and it's steel. And then this is 1 inch in diameter, tungsten. 2 different materials now with a stepped force increment. And I want to do 3 things. 1, I want to determine the stress in each bar. 2, I want to determine strain and deformation of each. And 3, if I label this A, B, and C, I want to determine the change in position of C. And just to make this a little easier, I'm going to not compute the stress because you guys know how to do that. Right, so just dealing with strains, deformations, and then a change in position. All right? So, how would you guys solve this? I want to hear your thoughts. what was step one of any of the problems that we solved previously? What do you guys remember? Yeah?
Finding the external, forces.
Right. Step one was always determine external equilibrium. Right? And the way that we do that is, let's just do sum of the forces in the x direction. Set that equal to 0. We've got 90 kips moving to the right, which means it's positive 90. We've got 30 kips moving to the left, so we add negative 30 kips. And then lastly, we consider this little boundary right here, AX. So we would just add AX to that. And what we would get is AX is equal to negative 60 kips, which tells us it's moving to the left. Does it make sense how I got that? Any questions at all about this so far? All good? Step 2 is what? Internal equilibrium. And the way that we do that is by drawing our internal force diagrams. So this diagram would stretch to here. We've got this at about the transition point from steel to tungsten. I think it's a little bit more in the middle because it's 12 and 12. So that's the transition point between steel and tungsten. And so what are we going to have? Well, we have 60 kips going to the left here, right? So it's moving to the left. So let's cut a section through AB, which is going to give us AB as what? In tension or compression, and what value? Let's just update this to then just be 60 kips. So you cut a section through here, draw it in tension. What is NAB? And remember, when you cut a section, you only look at stuff either on the left-hand side or on the right-hand side. Don't be including anything else. Yeah?
30 kips.
Nope. Let's cut a section. So let's draw our internal force diagram. We've got this bar here. We're cutting a section through it. 60 kips is moving to the left. And we've got NAB going to the right. What is NAB going to equal? In tension or compression? Tension. Why? Exactly. And if you were to do sum of the forces in the x direction, you would get that NAB equals positive 60, and the positive sign tells you it's in tension. So now we know that NAB is equal to positive 60 kips, which is in tension. We draw that on our diagram. You do the same thing for BC, And what you would actually find is that it's in 30 kips compression. Okay? One of the ways you can do that is just cut a section right here. Tension goes that way. So you would get a negative sign once you do NBC. So negative sign indicates compression. Everyone see that? From here now, we can now begin to compute the deformations that each bar feels from its own internal force. So let's look at bar AB. Let me label A, B, C. So for bar AB, this is for step 3, is compute deformations. And this would be like compute deformations, stresses, strains, just using whatever formulas we have. We did all of the difficult part now. Now it's just a matter of plugging and chugging into our formulas that we have now. So for the deformation of bar AB, our internal force is 60 kips. The length of our bar is going to be 12 inches, right? That comes right from here. What is the elastic modulus of steel? Because AB is a steel bar. Elastic modulus of steel, who's got it? I want somebody over here. It is 29,000 kips per square inch. And then what's the area? It's 3 inches in diameter, so what would the area be? You got it?
I guess 7.07.
Yeah. You compute that by doing pi over 4 times 3 inches squared, because the 3 was the specified diameter of the steel rod. And that equals 7.07 inches squared. So you just throw that right into here. And what we get for the deformation is around 0.00351 inches. I cannot keep consistent handwriting size. I'm so sorry. Does everyone get that for the deformation?
So if you put all of that into a calculator, you should get.
Yeah. So you should 60 times 12 divided by 29,000 times 7.07. You should get, 0.00351. And that's just a deformation, which means that the strain is magnitudes smaller. So remember when we said we wanted to determine the strains? How would we determine the strain of bar AB now? The strain felt by bar AB. Yeah. Exactly. So it's 0.00351 inches, the change in length, divided by its original length of 12 inches, which gives us a very small strain of like 0.0003. Very small. Let's do the same now for delta BC and epsilon BC. Take a few minutes. I want to see what you guys get for that. So I'm going to let you guys do that now. I'll walk around. Well, there's several pages for Appendix C. See, like right here, another one of them is just 2 pages back. Tungsten's not on that page. Is tungsten not on here?
I can't find it. So.
Tungsten's not on here, is it?
I don't think so.
Okay. Change. All right. Here's what?
Let's do some aluminum.
Aluminum. Yeah, I was just thinking that. You read my mind. So let's change this to be aluminum, but we got to pick an alloy, right? Because different alloys have different moduli of elasticity. So I'm going to say
Just do a combo. Make it easy for everyone.
alloy 7075 T6. In the future, I will give you guys problems on like exams or homeworks that you can actually use on the table. Yeah, these are my first semester lecture notes I'm using, so because of that, I just made things 10 times harder than I needed to. It's the very bottom aluminum alloy, just so I don't have to scroll up, yeah. Yeah. You got it?
I'm about to, but I'm just wondering, how did you convert, like I did this, but then how did you convert it into KSI?
So that is always going to be in PSI, so divided by 1,000 to get it into kips per square inch.
Oh,
Yeah, so if you always want this in terms of KSI, just
and then
10 to
divided by
Oh, one
1,000.
square.
10 to the 6.
Oh.
Yeah. I have no idea if that's right, but, because my solutions are based off of an entirely different material. But your procedure looks good. Just keep in mind the direction that this deformation is occurring. Is this gonna be in compression or tension?
Well, it was really negative, so compression.
Right, so you would wanna really express this in terms of negative values.
I didn't know if we kept it.
You usually wanna keep the negatives, right? It just makes sense. Yeah, try to, because then it just, yeah, it's either keep it as negative or clearly indicate like compression tension by C or T.
Okay, so then just put a C for these?
Yeah.
Thank you.
All right, let's go over it, then you guys will get your break. You're almost there? Should I wait a few more seconds?
Yeah, we'll swap, but I wanna figure it out.
All right, I'll wait. 60 seconds.
Yeah, you do that.
Yeah. Yes. Strain is unitless. Yes. Usually you would express, it sometimes expressed as inches per inch,
Oh, yeah, that's
but you
that's for.
usually just ignore that. Some people would write like inches per foot if they didn't align the units. That's technically correct, but people will get pissed off and it messes up the mathematics. So just keep strain unitless at all times. It just makes the math so much easier. Yep.
Yeah,
You did a diagram, positive 60. Yeah, so you can do a separate cut and you can find that it's negative 30, which is how you get that part. So the force is negative 30. Exactly.
so much stress. Yeah, because it all cancel out.
You get it yet? Waiting on you.
Yo, I see you're good.
Okay, alright.
Sorry. Thank you for waiting, though, I appreciate it.
Of course. Alright, delta BC. The equation would be NBC, LBC over EBC times ABC. The force in member BC, negative 30 kips. The length, 12 inches. The elastic modulus of this material would be 10.4 times 10 to the 3. So 10,400 KSI. And then the area, you would just pi over 4 times 1 inch squared. You would get an area of 0.79 inches squared. You should get a deformation of negative 0.0438, 2 inches. The strain you would just divide it by the length again, which gives you negative 0.004. Or I'm going to expand it out as much as I did the previous one. 0.0037. All right. And then lastly, we were asked determine the change in position of C. What do you guys think the change in position of C is? Who here thinks they got it? I get the change in position 0.04031 inches. Negative. Who here gets that? You do. What did you do?
Added just the,
Exactly. So you just add the deformations of each bar from the fixed point. So if you wanted to find the change in position in B, it's just going to be the deformation of rod AB. If you wanted to find the change in position of C, it's the deformation of rod AB plus the deformation of rod BC. And you keep on adding the deformations you compute for every stepped rod that you have. So if this was like 50 of them and you wanted to find the deformation at the far end, just add everything together. Does that make sense? All right, let's reconvene at like 7:15-ish. What I just did. All right. So about 7:20. 7:20 we'll say. Just so you guys have a bit longer. Oh, you guys are gonna hate the exit activity. Yeah. Yeah.
On the homework.
Okay. What's the question?
Oh, it's about question 3.
All right.
Because it said that there 6 holes were drilled.
Yeah.
So is that like what we did in class? When we multiplied
Here, let me just get to it first.
what's this question? It's like a simple hole, but in this case there was a total of 6 holes drilled. There are 2 holes in each place.
2 in both flange, 2 in the web, 2 flanges each. So there's 4 holes in all of the flanges combined. And then 2 in the web. So 4 plus 2 is 6.
Right.
Yeah. And then I asked you to determine the stress at that cross
Yeah, because
section.
right now we did in class with this question.
Right.
Because I feel like these are similar.
Yeah, they're identical basically.
So,
Just cut a section
mhm,
and draw out how the holes would look in that cross section.
right.
Right. What did we determine from cutting the cross section how the holes would look?
The rectangle.
It was rectangular in cross section with dimensions of the diameter times the thickness of the material. So there, you're gonna have 4 bolt holes. So you would take the diameter of those bolt holes, multiply it by 4 times the flange thickness. And then for the web, it would be 2 bolt holes times the diameter times the thickness of the web. And that's the area that basically gets
You add
trapped.
those together.
Yeah. Make sense?
Yeah, I got it.
Yep. And what's your question?
It's not so much a question, but, this is the first one. I know that you had all the questions, I hadn't opened it or looked at it.
Okay.
I had finished this before.
Yeah, no worries.
So,
Alright, that's it.
And then I just have another question on this step two.
Yes.
How do you get that 60 kips? Because if the A1 is equal to,
These 60 kips comes from this little thing right here.
so you have 60 this way. and
Yeah,
then
this is the reaction force, which then you basically apply as like a separate force that comes on the structure. And then once you cut a section through here, eliminate everything on the
right
right,
hand side. So that's why it's 60, because we're only
Right.
considering
on the left.
the left hand side.
Yeah.
Okay.
Now, if you were to look at it from this right side perspective, right, you would cut a section right through there.
Okay.
Eliminate all of that and draw a tension force. And just like that. So you would get a net of 60 kips
so then it would be 3/4.
to the right, from the 90 minus the 30, 60, which means N needs to be 60 going that way anyways, which gives you tension.
Okay.
So,
Okay, yeah, because I guess, I don't know what I was, I understand like everything else, it was just that step, because I did 90 and then minus
So 2.
60, and then I was like, oh, I got 30 kips, but I was like,
Right.
I don't think you have to.
yeah, that's why I always cut the section right at the center.
Okay.
And then just disregard anything on either side would.
Exactly.
Okay, makes sense.
Yeah, and you can always check both sides too. Sometimes on the exam, you might, be crunched for time, but if you get good at like cutting the sections and you want to like check it, just check going the opposite direction.
And then 4 of
Okay.
0.515
Yep.
times the 3/4. Yeah, but it's just because we didn't have any in the flange, it was just the left.
Depends on what they were, but they're on my nose. Or I'm listening to the, yeah, that's one of the ones.
Okay.
So when you're solving for the moment, for the reaction for GUI,
Mm-hmm.
you would do times 30, right? Because this part wouldn't count, right?
GY. So this is sum of moments. -5
For the,
times. Where are you taking the moment from?
this one is from for F of Y. So
Right, but you shouldn't be multiplying any lengths.
right.
So here's a nice little trick. 5 kips going down that way, 5 kips going down that way. They both have the same moment contribution, which means all the force is going to be concentrated at G.
Right.
It's not what you're showing here. Yep. So make sure to clearly not multiply when you're doing sum of the forces in Y or sum of the forces in X. There should be no multiplication going on. So it should be just -5 plus gy plus ay minus 5 again. You have two unknowns, so take a moment. Take a moment about g. You would find ay is 0. Or take a moment about a. You would find that gy is 10.
Okay.
All right?
Yeah, that makes sense. Thank you.
All the bad people to the US.
Now, the Germans are sick, other people that get drunk and function. Same with the Irish.
Sure.
Yeah, if you want the coffee, it's over there. I swear to God, I didn't disrespect.
All right, I graded it. I forgot to bring all of the homeworks today. I have everyone's graded. I am so sorry that I forgot to bring them in. I will bring them in next class. Send me an email reminding me in the event that I end up forgetting again. Otherwise, I will personally scan everyone's homeworks as much as I don't want to, and I will send them to you. Just so you guys have them. But everyone saw their grades, right?
Unfortunately. No, my grade was BS.
What?
No, it's because you, like you said, I messed up with the one number, so I threw everything off, and I think you know.
I try not to carry stuff through. So if you mess up a number and do everything else right, I try not to double count errors because I try and look at your methodology that you're doing.
Alright, so then I must have messed up more than I thought I did too.
Probably. Because I don't, because what I do is like, this is why like when you guys are solving problems, try and write the equations too, instead of just throwing the numbers in, because it makes it a heck of a lot easier for me to make sure that you guys are following the right steps, or at least for me to check that you guys are following the right steps.
Doing that.
Yeah, probably.
Yeah. There's an E there.
Yeah, I got worried. I thought I kicked it out.
I did that today. It's what it is, probably.
All right. Now, let's get back to this. So, now I want to just ask you guys something a little bit different. All right? What I want to ask you guys is, what is the factor of safety of each material? All right? You guys learned a little bit about what the factor of safety is from your previous exit activities, right? What did you guys do with the factor of safety? You just multiplied it by whatever the force was, and then you checked it against the capacity. The true definition of what the factor of safety is, we call it FOS, is it's a ratio of the capacity over the demand. So, a way that we can think of this is sigma y, the yield strength of the material, over sigma, where sigma is the applied stress in the material. So sigma y is a material property. Sigma is the applied stress. If you had bolts, for example, and yielding wasn't really a concern in the design, so for example, bolts, remember how I was saying for bolts you use the rupture strength for it, then sigma y would just be replaced with sigma u. But in cases where you're designing really long elements, really large scale elements, you use sigma y. These would be for like beams, columns, tension members, basically anything that's really large scale. Anything that's smaller scale that's not going to deform an immense amount, you just use sigma u, which is that ultimate strength that we were talking about previously. So in this case, we've got these really large scale bars here. What's the strength that we want to use to check that it doesn't fail? Sigma Y or sigma U? Yielding or ultimate strength? Yielding. So let's determine what the factor of safety is for each, the steel and the aluminum. So for the steel, what is the yield strength of the steel that I gave you guys? Did I tell you guys something? No. I don't know. Let's pick a steel type.
We're using the structural one, very top one, 36.
Yeah, so we'll use steel, and it's A36. So the yield strength of steel is going to be what? 36 KSI. And what's the applied stress? Do we know that? Yes or no? We can compute it because we have everything we need. We just don't know it off the top of our heads because we didn't calculate it. So let's calculate it real quick. Sigma is equal to the internal force of the steel, which was bar AB. So that's going to be 60 kips divided by the area, which was 7.07 inches squared. You do the math, and you get a factor of safety. Oh, wait. You get a stress of 8.49 KSI. So now you just throw it back into this equation up here, and the factor of safety you should get equal to 4.24. Most structures are designed with a factor of safety ranging anywhere from 2.5 to 3. Those would be like bridges, buildings. Anyone want to take a guess what the factor of safety for an airplane is?
You told us yesterday, like 2 or something.
Oh, it's less than 2.
1?
It's like 1,
Like,
near 1. It's like 1.1, I believe. So they use very advanced methods to try and get very precise numbers. Why do you think the factor of safety has to be really small? Exactly. If it's too heavy, it uses up more fuel, which makes it very uneconomical for use. So planes are generally very safe with about a 10% margin of error. So actually, I laughed about that during my graduation speech because I had never been on a plane before senior year of college. So when I was going off the runway, I was just saying to myself, these students that in my graduating class did not design it, an actual engineer did, I should be okay. Because God forbid one of the students that I was graduating with designed it, I'd be killed. All right, let's do the factor of safety for the aluminum now. What's the yield strength of the aluminum that we specified? 73 KSI. So we need to compute the stress. So we've got negative 30 kips. Divided by an area of 0.79 inches squared. And what we get is negative 37.0 97, so I'm just going to round it up to negative 38 KSI. Now, here's the thing. When it comes to these materials, the yield strength, I guess, acts okay for both tension and compression. So I really don't like how they have it specified here that the yield strength is only for tension, because the yield strength is generally for both sides of tension and compression. So I would just say, instead of tension, just cross it off and put axial, because the yield strength is the yield strength for the material. Now, ultimate strength, that's an entirely different situation, because once a material yields, there's a ton of things that kind of go into the nonlinearity of it. But for a linear region, they should remain the same. So, really, the yield strength of this material, just put a negative sign. Negative 38 KSI. And you get roughly a factor of safety of 1.92. Are there any questions about that? Do you guys understand why we put the negative sign? No? The reason being is because I'm kind of just telling you guys, like, just change it to axial, which means that it could be both tension and compression. So a compression would just mean that the yield strength, the sign would just be negative. So it's really the value that kind of matters here, and it's up to you guys to decipher if it's tension or compression, because in practicality, you cannot have a factor of safety that's negative. It just doesn't work. It's either it's in tension or compression, because then at that point, you're comparing a tension capacity to a compression load. The two are entirely two separate things, so it just, you can't do it, right? All right. Are there any questions about anything we talked about? Do you guys feel comfortable about determining the deformations of these bars here? Everyone feels good? If I were to give you guys an exit question right now, you guys think you can do it? Good. All right. Well, I'm going to give you guys the exit problem now because I threw a truss on here. All right? Because I know you guys love trusses so much. For you, for you, for you. For you. Let me stop this.